is a third lecture by Lee. His title is KAIST groups in real projective geometry.
Okay, so thank you. So let's continue to the third lecture. So this is the last lecture. So the second lecture, we'll learn how to produce this nice representation from the KAIST polytopes. Okay, and also lastly, we learn this theorem, which is about when my reflection group is convex co-compact with some assumptions. And let's go to the one more nice theorems, which is Davis and Charney-Davis. So the reason I introduced the theorem, because when we want to show that some interesting quasi-function representations, which is not, this group W is not the uniform lattice, then we need these theorems. So let's look at these theorems. The theorem. So the Davis and then the Charney-Davis. So as usual, and WS is my KAIST system. And we have a faithful representation, let's say tau. And suppose this tau W act discontinuously and co-compactly on some properly convex open set omega of SV, then first for all S, then the tau S is a projective reflections. And then tau W is in fact the projective KAIST group generated by the reflections tau S in S in S. So what is the points of these theorems? The point of this theorem is the following. This discrete group acting co-compactly on this omega. Okay. But then this guy should be in fact a reflection. In general case, if you imagine, every element and every generator in W is a involution, meaning that the image should be also involution, but the involution can be various involution, right? What I'm saying is that it's conjugate to, for example, let's say the V is dimension 4, then it can be a 1, 1, 1, minus 1. So it can conjugate to the following this one, but also it can conjugate to 1, 1, minus 1, minus 1. Okay, but this one is not the reflections. Okay, it's simply the involutions. But the point is that this group act co-compactly. This is very important. But then this is not happens. It should be the projective reflections. And also this whole group is really produced by the KAIST polytopes. So that's the point. Okay, so then using this Davis, Charney-Davis, let's show the following proportions. So the W, you remember my W, it was this one, 7, 7. My W is not isomorphic to a uniform lattice of isometry group of HE for any E bigger than equal to 1. Okay. So you see, so I want to show that this W is not isomorphic to the uniform lattice of the isometry group of hyperbolic space. Then I think we have this counterexample for the questions I mentioned in the second lectures. Okay, so let's go to proof. So how we can show that? So first, we fix the points in XE, and then look at the orbit map. So the orbit map, okay, so since the orbit map I, which is W to the HE. So what is the orbit map? If I take the gamma, then tau gamma is the elements in an isometric group of a hyperbolic space. So I can multiply to the points x0. Okay, then this is a points in HE, and then this orbit map is quasi-isometric. Okay, so maybe I think I didn't really write the previous saying. So, okay, because I said that, it might be, sorry. So I said that W is not isomorphic to the uniform lattice. So I think let's assume, so by contradictions, I think I should be saying my first this one. By contradictions, there exists a faithful representations. Representation tau. Okay, this is my tau from the W to the isometry group of HE. Okay, whose image is a uniform lattice. Whose image is a uniform lattice. Okay. So assume on the contrary that there exists a faithful representation tau. Okay. Then, okay, let's pick the points in the hyperbolic space and then take this orbit map. Okay. Because this is uniform lattice, meaning that this action is co-compact actions. So this is quasi-isometric. So it extends to a homeomorphism from the boundary of the group to the boundary of the hyperbolic space. Okay, but boundary of this hyperbolic E space, of course, homeomorphic to the E-1 dimensional spheres, but we know that this boundary of W's. So what is the boundary of this W? When we have this group, what was that? It was, so if I take this group, I think we compute the boundary of this W, right? In first lectures.
Yeah, I forgot.
So yeah, okay. So I think
I think the boundary is a D-1 dimensional sphere, if I remember correctly. Yeah, because this is an abstract This is an abstract geometric reflection group of dimension 4.
Yeah. So so here to compute the boundary, we should look at the nerve. But the nerve, what was the nerve? Nerve was join of S1.
The nerve is S3, yeah.
Yeah, exactly. So you are right. So it should be also the S3.
Yeah.
Okay, so E is equal to 4. Okay, so because this tau W is a uniform lattice, of isometry group of H4. So it satisfying these assumptions for this Davis and Charney-Davis theorems. So it implies that this my group tau W is a projective Cox group generated by the reflections. Okay. So it's tau S will be the identity minus some quadratic form, let's say Q PS dot PS. Okay. So here, so if you remember this Cox group, we have a 6th generator. So it should be for some 6 vectors VS of R41. Okay, so here isometric over H4, so the R41 with, of course, Q VS VS is equal to 2, and then this Q is a quadratic form on R41, defining POD1. In this case, D is 4, right? Is 4, 1. Of course, this is isomorphic to our isometry group of H4. So you see, here the R41 is a dimension 5, but here the 6 vectors. So it means determinants of the CW. So this is, of course, the Q VS VS. So the S, the VS, sorry, the PT. So ST is in S, should be a 0. So once again, this is the vector space is dimension 5, and we have 6 vector. So no matter what, this determinants should be 0. But so the determinant of CW, if we compute, then this is non-zero by computations. In fact, as I said, that the signature, so in fact, the signatures of this cosine matrix is 5, 1, 0. Okay. So this is contradictions, right? So this is end of the proof. So here the essential part is again this Davis-Charney-Davis theorems, saying that here, because we have a uniform lattice, so the action is co-compact on H4. That's why this group has no choice. This group should be the reflection group generated by these reflections. And then the remaining part is kind of obvious because the 6 vectors in R41. So if we take the determinants, then this should be 0, but by the computation, this is non-zero. This is contradictions. So in this way, we construct the interesting Cauchy function representations from my favorite Cox group, this guy.
May I ask a question?
Yes, sure.
Yeah, so just to make sure, in the second part where you say that the determinant of CW is non-zero, you compute the determinant with respect to the cosine matrix associated to WS?
Yes. Yeah, because this guy with, so it should be what? So it was something like this, W. So I do one more time, 7, right? So the CW should be something like 2, 2, 2, 2, 2, 2, right? And then, okay, so let's do that. So 2 times cosine pi over 7, and then minus 1, minus 1, minus 1, 2, 3, 4. Oh, did I miss 1, 2, 3, 4, 5, 6, 7? Okay, so that's why I need one more 2, and then minus 1, and then minus 2 cosine pi over 7, and then all 0, and then there are same thing here, right? Okay, and then I computed the, in fact, even we can compute the signature, but in any other determinants, then this is non-zero.
Okay.
Because here, there is no infinite label, right? So there is no other choices. It should be these numbers. Yeah, and then here's the 0. So there is no choice. That's why I think we can easily conclude that. So this is non-zero, and then yeah, we are done. So that's good. So we produce nice this convex co-compact, I mean the Cauchy function representations. Okay, but some people want to have this representation for the fundamental group of manifolds. That's always people interested in more, because the reflection group is, I think, is very nice, but it has a torsions. So to upgrade this to the manifold group, I need some more things following. The theorem by the Tukia. So the gamma is a finitely generated group, and G. So in fact, when the G is semi-simple Lie group, there is a similar theorem, but we need to add more author. There are long list of the author, but for the hyperbolic space, I need to just mention the Tukia. Okay, so then, so the gamma is finitely generated group, and G is isometric group hyperbolic space. Then the following two statements are equivalence. The gamma is Cauchy isometric to a uniform lattice of the isometric group of hyperbolic space if and only if there exists a representations tau from the gamma to G with the finite corner and whose image is a uniform lattice of G. Okay, so there are these very surprising these relations between the Cauchy isometric to the uniform lattice and these representations. So the gamma to G, but here finite corners. But it's interesting to see that for the Cox group, is a proportion by the Paris, that this finite corners should be the trivial. Why is that? This might be Paris. I should write name properly, the Paris. So the when W is irreducible, large Cox group, if N is a non-trivial normal subgroup of W, then N should be infinite. Okay, so the N is non-trivial normal subgroup, then N should be infinite. So the corner is, of course, the normal subgroup of gamma. Then it should be, it means that it's finite. We can upgrade when this gamma is irreducible large Cox group by the trivial corner. It means that we have a faithful representations. Okay, so for the Cox group, it's surprisingly, the gamma is quasi-isometric to the uniform lattice if and only if we have a faithful representations whose image is uniform lattice. Okay, so why we can use this theorem to upgrade the previous propositions, this one, to the manifold group. So the story is the following. So the W is a Cox group. Okay, so there exists the finite index subgroup, which is torsion free. Okay, so it will be the manifold group. So, but this finite index subgroup, so maybe I should write W is inside the torsion free subgroup W prime. Okay, but I want to say that W prime is not isomorphic to the uniform lattice of the isometric group HE because of this combination of the two Kia and Paris. Okay, because if W prime is a isomorphic to the uniform lattice, then it means that W prime is quasi-isometric to a uniform lattice. And then W prime and W is just finite index. So W should be also quasi-isometric to the uniform lattice. But to Kia say that this should be, we have this representation from the W2, also this G, whose image is a uniform lattice, which is a faithful representation, right? Okay. So then there is contradiction, right? That's, we said that there is no, this W is not isomorphic. Okay. So my point is that it's up to finite index is make no change for this quasi-isometric, this property. So we can upgrade to the manifold group, which is a finite torsion-free, finite index torsion-free subgroup of W. Okay, so that's the thing I want to mention. Okay, so is there some questions? So this is actually end for the second part of these lectures. Okay, so then let's go to the third part. So I want to mention the 10 fillings. Okay. So this 10 filling has a motivation to construct another interesting example of this, the Cox operator. So what is the motivations? So the motivation starting from the Thurston and filling theorems. So what is that? So if you have the interior of compact free manifolds, if the interiors of a compact, the three manifolds M with the Tor boundary admits a compact, sorry, the compact, not the compact, it's complete hyperbolic structures of finite volumes, then all, okay, so almost all then fillings of M admits hyperbolic structures. So I think it's better to draw the one particular example. So let's look at the figure 8, not the figure 8, not. So the drawing will be, so this is the figure 8 not in S3, okay? And then take the open neighborhood, so tubular neighborhood. So maybe I think I should use the same colors. So okay, so did I? Yeah, okay. So the tubular neighborhood, okay? So this is okay. So then, so this is of course the compact 3 manifolds with torus boundary, okay? And then of course the interior will be simply the figure 8 not complements, right? But in anyhow, so here what is the then fillings? So the then filling is, you imagines the solid torus. So the solid torus has also torus boundary, which is also this is compact 3 manifolds, right? So it has the left-hand side, it has also the torus boundary, and solid torus also has a torus boundary. So we can glue these 2 3 manifolds to get the closed 3 manifolds without boundary, right? The closed 3 manifolds. But of course, there are several ways we can obtain this then filling. So that's we call the then fillings. But except the finite number of them, all of them admit the hyperbolic structures. Okay. So that's certain then filling theorems. But it happens only for 3 dimensions. So when the 3 become the n bigger than or equal to 4, then we cannot have such a theorems. Even though we can also think about the similar situation, because you imagine the compact n manifolds with a torus boundary, and then we can also think about the higher dimensions solid torus, so we can glue together, right? And then we obtain again the then fillings for the higher dimensions, but these then fillings does not admit the hyperbolic structures when the dimension is bigger than or equal to 4. Okay, so the questions is that the questions is that, okay, so the hyperbolic structure we cannot do anymore. So how about the properly convex structures? So the question is, M is the same setting, so the compact and manifolds. So n bigger than or equal to 3 with the toral boundary, such that the interiors of M admits a finite volumes hyperbolic structures. Then do almost all then fillings of M admits a properly convex projective structures. Okay. So might be for the remind you the what is the precise definition of the admits properly convex projective structures. So the manifolds M admits properly convex projective structures. So this is the definitions. If M is homeomorphic to the omega quotient by gamma, where the omega is a properly convex subset of Sn. So the properly convex subset, it means that take the closure, then it's a bounded convex set in some particular affine chart. And the gamma is a discrete subgroup of SL plus minus M plus 1 R acting properly discontinuously on omega. Okay. So if you remember in a previous setting, in a projective Cox polytope, then of course when we have a omega and then the gamma will be the Cox group or the reflection group more precisely. And then the quotient is not really the manifold, but we have a properly convex projective ovifold. But in anyhow, if I take the finite index, the subgroup of the Cox group, which is torsion free, then we obtain this kind of setting, right? Okay. So this is the questions, and then these questions will be the very interesting, but still it's not really solved. But we found some interesting example using a reflection group. So that's why I want to give this third lectures. So look.
May I ask a question?
Yes.
So in the statement, almost all means just except finite element cases.
Yeah, except the finite dimension. Yeah, that's true. Yeah.
I see. Thank you.
Yeah, you're right. Thank you. But here that's a question. Also, as I said, it's not really solved. So I don't know what will be the really theorems, but I hope that except the finitely many, all of them admit the properly convex projective structure. That's my hope, but I don't know in manifold case. But especially in our the polytope case, there are some example which is actually such a consideration is true. So look at the G. So G is I denote, which is a combinatorials, the polytope together with Rich labeling. So and each rich E, I put theta E, which is pi over M. So the M, 2, 3, and infinity. So the combinatorial polytope together with the Rich labeling. So here the Rich, of course, the phase of codimension 2. Okay. So this is a labeled polytope. Okay. The combinatorial polytope with the Rich labeling. So that's why I call the labeled polytope. Then, for example, we can think about the following space. which is hyperbolic, the space of hyperbolic Coxeter polytope realizing G up to isometry group of H n. Okay. Okay. So of course, when we have this n-dimensional polytope. Okay. So if you're familiar with this OV4, then this is basically the same thing as a deformation space of a hyperbolic structure on OV4. But I think to ignore this definitions, it's a technical definition for the OV4s, but I rather use this labeled polytope, and this space HG is a hyperbolic Coxeter polytope realizing this labeled polytope. So let's try to give first in dimension 3. So the Andrew theorem. In fact, the Andrew theorem is really important theorem in a hyperbolic 3-dimensional this polytope theories. And these theorems, probably the stating that this theorem is we need some time. So I rather just mention some particular example. So which is the following. So let's look at this one, and then okay. So I draw some combinatorial polytope. So right hand side, this is simply the pyramid over this fourgon, and then the left hand side we have a triangular prism, right? And then I give the ridge labeling. So here the ridge is edge, right? So I give the labeling. So how we can do? I just give, for example, here pi over 3, here pi over m, and here pi over 3. If I didn't give the labeling, I mean the pi over 2. I think you can guess. So for example, here the pi over 2, but I didn't write because then it might be more complicated. So similarly here the pi over 3 and pi over 3. Okay. So this labeled polytope I will denote by GM. Okay. So the triangular prism is a combinatorial polytope together with the edge labeling. Okay. Pi over m, pi over 2, something like this. And then the right hand side is a G infinities. Okay. Okay. And then if you have this labeled polytope, we can easily imagine the Cox group. Okay. So how we can do that? 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so the 1, 2, 4, 5, 3. 1, 2, 4, 5, 3. Okay, so maybe I think I try to explain. So, for example, here the 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So if I look at this is a phase 1. So the phase corresponding to the vertex in a Cox group or the Cox diagram. And then this is 2 and this is 2. So the phase 1 and 2 are adjacent. And this angle or the label is pi over m. So I put this h and then the label m. And for example, in 2 and 3, so here this is 3 and 3 and 2 and 3. Again, the adjacent and the angle is pi over 3. So I put here the h and then but I want to also put 3, but okay, usually we omit this 3. Okay, so similarly we can do, and then here also we can do, because in the right hand side, the 1 and 2, these two faces are not adjacent, right? So that's why here the infinities. Okay, so makes sense. So from this labeled polytope, we obtain Cox group Wm and W infinities. Okay. So then the Andrew theorem is the following. So the theorem of Andrew. But once again, I want to mention that Andrew theorem is really the general theorem for the hyperbolic three-dimensional polytope. But this is just examples, okay? But if M is a 7, 8, and infinity, then there exists a hyperbolic polytope PM realize GM. Okay. Otherwise, HGM is empty. Okay. So there is no such a hyperbolic Cox polytopes. Okay. In fact, so these conditions is really the necessary conditions. We can easily see from these pictures. If you imagine the hyperbolic polytope which realize GM, okay, but then if you think about this, some hyperplane which passing through these triangular prisms, but then this guy is a hyperbolic triangles whose dihedral angle is pi over 3, pi over m, and pi over 2. So hyperbolic triangles, the angle sum should be less than pi. So m should be bigger than equal to 6. So the bigger than 7. Okay. So I'm right. So pi over 2 plus pi over m plus pi over 3 is less than pi. So from this, the m should be bigger than equal to 7. Okay, but the key part of the Andrew theorems, so that this part is quite easy, but the key part of the Andrew theorem is that that's enough to guarantee that your labeled polytope will be the realized by the hyperbolic polytopes. Okay. So yes, so that's why, because we have now the hyperbolic polytope, then we can produce the reflection group, okay? And then the reflection group is actually produced by representation. So maybe I should use a different colors. So representation W infinity to the isometry group of H3, okay? And then the Wm. So what is the relation between the W infinity and Wm? Simply the Wm is a W infinity quotient by the least normal subgroup containing S1, S2, Dm. Okay. So we have this. So this is rho m, and then the gamma m is the rho m W infinity. So then we can actually check that these intersections of the PM and H3 is a fundamental domain. For the gamma M, these actions. And then, as I said, Oh, no, I didn't say it yet, but I will say that this when is between the 6 and infinity is not infinity, then this PM is inside hyperbolic space, and so the gamma M is a uniform lattice. In the isometry group of H3, and if M is infinity, then there is intersections with the boundary, which will be the vertex. So maybe I should draw this vertex here. This vertex. Okay. And of course, this gamma infinity is a non-uniform lattice. Okay. So maybe I think I should explain what's the relations between these certain fillings. So the right-hand side, so you have this this guy. So this guy is a three-dimensional hyperbolic Cox polytope. This particular vertex, this is ideal vertex. So you can see that if you look at the link of this vertex, what you see is rectangles, because I didn't put the label, it means pi over 2. So the rectangle is the right angles, the right angles, rectangles, right? And then, but if we perturb this configuration a little bit, because at the beginning it was the vertex of the valence 4, but if we perturb, it can be something like this, or it can be something like that. Okay, so this is some picture, right? If you look at the following here, around. So if you look at the left pictures, now this triangular prism is in fact compact three-dimensional hyperbolic polytope in hyperbolic 3 space. Okay, and then when M goes to infinity, so M equal to 7, A is getting bigger and bigger, then this edge is shrinking. In some points, it's become this ideal vertex. Okay, so from here to here, the right-hand side is a complete hyperbolic polytope, and then the left-hand side is a compact one. So from the right to left is a polytope versions of den fillings. Okay. Of den fillings. So sometimes from the non-compact polytope, we can obtain a compact polytopes. Okay. Okay. So this is a dimension 3. Okay, so the Andrew theorems. So from this, we can easily see the following corollary is that for any neighborhood U of rho infinity, which is in the whole W infinity and isometry group of H3, then there is rho in this neighborhood such that rho is not conjugate to the rho infinities. So of course this rho, for example, the rho M, if I choose a rho M, it's not of course the conjugate to rho infinities. So here this rho M is basically we need to find this the interesting examples. Okay, but the following theorem of the Galland-Lagunatans saying that this is not happen when the dimension bigger than equal to 4. The theorems, Galland and Lagunatan, T, then the D is bigger than equal to 4, and the gamma is lattice in an isometry group of HD. Then there is a neighborhood U of the canonical inclusions. The inclusions, the low infinity in the home gamma and isometry group of HD, such that for all representation in U, that rho is conjugate to the low infinity. Okay, so the previous situations never happen in dimensions bigger than equal to 4. So we need to change this group, isometry group of hyperbolic D space to, so we need to change this to the SL plus minus D plus 1R, which is projective geometries. Okay. So let's try to give at least one nice examples. So previously in dimension 3 polytope, I project to the planes to draw, right? But now the 4-dimensional polytope, I project to the 3-dimensional space. So first one, let's, okay. So here, so now I draw the triangular prism, right? And then the cone over this triangular prism. So the triangular prism we can write as a delta 1 cross delta 2, because the delta D is a D simplex. So the delta 1 cross delta 2 is a triangular prism, and then take the pyramid or the cone over this. So this is this vertex is exactly the apex. Okay. But then if you perturb this polytope a little bit, but then we can obtain the following polytope. So what it should be something like this. So what happens? So if we look at these small triangles, these triangles, so when this triangle is shrink, then it will be this vertex. So what is this polytope? This polytope is a delta 2 cross delta 2. So the triangle times triangle. So triangle times triangle. So for example, the face will be triangle times interval. This will be the face of codimension 1, which is facet. So for example, you can see here. Okay. So this will be the corresponding the facet. And then this is another one. Okay. And then these two facets are adjacent, and this intersection is exactly this blue triangles. Okay. So this is the combinatorial polytopes, and I want to give the rich labeling. So how we can do? So that will be the GM, that will be the G infinity, right hand side. So instead, draw this labeling on this picture because it will be messier. So I put this corresponding Cox diagram. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So this will be the pictures. Here I will give the M, and this is infinity. So this green facet will be corresponding to this vertex of Cox diagram, and this green facet will be corresponding to this the vertex of the Cox diagram, and similarly this vertex corresponding to this facet, and this vertex corresponding to this facets. Okay. So then I put the M. It means that here these two facets are adjacent, and the dihedral angle is pi over M. Okay. And similarly, we can give the labeling corresponding to this Cox diagram. Okay, I think you understand what's going on. So this is a W M, and this is W and infinities. Okay. So this is my label for polytopes. Okay. And then as we describe this the HG, also we can similarly define a CG, which is projective the Cox polytope in Sn, realizing G up to SL plus minus M plus 1R. Okay. And then the theorems. So the Professor Choi and me and Marquis, 2020, for M is infinity, and this space of projective Cox polytope in projective sphere realizing G is equal to the hyperbolic polytope realizing G, and this we know that there it is, the hyperbolic polytope. In fact, this part is by the 2 markings, 2004, and then similarly for when the M between 6 and infinity and CGM has PM or PM star. So there are 2 projective Cox polytope realizing GM. Then otherwise is empty. Otherwise, the CGM is empty. Okay. So because of this, we can produce the representations 5R, and then the WM, it will be the similar. So W infinity quotient by this least normal subgroup generated by S1, S2M, and then here, and then this composition is rho M, and then my gamma M is rho M W infinity. And then if M is infinity, then this omega infinity, what is this? The interior of the gamma infinite orbit of P infinity is hyperbolic space, so it's ellipsoid, right? And this omega infinity quotient by the gamma infinity is of finite volumes. And then the seconds, if the m is between 6 and infinities, then the pm is inside omega m. Okay, because omega m, of course, the interior of the gamma m orbit of pm, and this omega m quotient by gamma m is compact. Okay. So here, if you look at these pictures, at the beginning, this blue vertex is an ideal vertex in this hyperbolic space, and this is a hyperbolic polytopes. Okay, and then the left-hand side, of course, you can see that here, this guy, this is a 3-3-3 triangle group, right? So this is it contains this WM contain a free abelian group of rank 2. Okay, but still, as I said, M is bigger than 6. There exists some projective Cox polytope realizing this GM. So here the M goes to infinity, then the left side picture will converge to the right hand side. Okay. So in this way, we can produce the new example compared to the previously known example by the Yves Benoit. The Benoit, okay, maybe I should write properly. The Yves Benoit in 2006. So Yves Benoit construct the interesting example from this tetrahedrons. So pi over, okay, so the pi over 3, pi over 3, pi over 3, and pi over 3. So this is a hyperbolic tetrahedrons, and this vertex is an ideal vertex. So you can imagine something like this. Okay. So this is a ideal vertex. But of course, you cannot deform. So you cannot change the hyperbolic, this tetrahedron inside hyperbolic geometries. But we can change in a projective geometry. So what I'm saying is that if you think about the projective Cox polytope, and then you can change the Catan matrix such a way that this vertex, I mean this polytope can change, and then you can actually truncate this vertex. So what I'm saying is that we can obtain so that this is pi over 3 and pi over 3 and pi over 3, and here the pi over 3. So exactly same, except this around the link, right? So if you look at the around the link, okay, here you have this 3 triangles. So I truncated this vertex, then we obtain this, and then we can make as a compact triangular prisms in the projective geometry. So there exists a projective Cox polytope realizing this labeled polytopes. Okay. But what is the main difference? Here, this is a three-dimensional objects, but this 3-3-3 triangle group is produced the free abelian group rank 2. So the co-dimension one, but in this case, we have a co-dimension 2, right? This is a 4-dimensional objects, and then we have this 3-3-3 triangles. So I think for the then filling, I think I stop here. So do I have some more time, or I should finish?
I think you should finish here. Yeah.
Okay, so thank you. So I think I stop here. Is there some questions?
Yeah, I do have a question just regarding the very last thing that you said.
Okay.
Yeah, so you mentioned that if you consider, for example, that tetrahedron in hyperbolic space, you said that you cannot deform it in hyperbolic space, but you can deform it in projective geometry. Could you explain maybe a bit more precisely what that means?
Okay, so thank you for your questions. So if I take the corresponding kata matrix, then what will be? So okay, so it's better to write the number. Let's say 1, 2, and 3, and 4. Okay, so then what happens is that so 2, 2, 2, 2, and then -1, -1, -1, -1. And then what happens? 3, 1, and 4. So here, right? And then everything is 0, isn't it? Does it make sense?
It makes sense.
Yes, exactly. So this is a corresponding the kata matrix, which is symmetric. But now I can do the slight change t, and here I change 1 over t. Sorry, here the 1 over t. Okay, so this is still the kata matrix in a projective geometry, right?
Yes.
It's not anymore the symmetric, so we cannot have this hyperbolic space, but it's okay. It's a kata matrix. So in fact, in this case, we have some tetrahedron, but it's a different tetrahedron than the original one. So then what happened is that, in fact, so these 3 reflection vectors corresponding to this phase, and this one. So then it has, so maybe I should write maybe this one. So then it has a hyperplane which contain these 3 reflection vectors. Then if I have something like this, okay? So this will be the corner of the new linear functional alpha, and then this will be the new reflection vector b. Then it will produce the new reflection sigma. Okay, so now then we have this picture, right? Because now this black face is corresponding to this black one. So in this way, so here we have this parameter t, and then when t equal to 1, it's exactly that is hyperbolic situations, but t is away from 1, then we can actually truncate this vertex, and then using that, we obtain this new 3-dimensional polytope, which is Cox polytope. So yeah, that's the stories.
Yeah, I see. And you need the matrix to be symmetric for the polytope to have a hyperbolic structure then?
Exactly.
Yeah. I see. Thank you.
Yeah, but I think your question is very good. So here, I didn't really describe precisely, but here we need to use this description of the kata matrix.
Yeah, okay, I see. Thank you very much.
Thank you.
So if there is no sort of formal question, we can join it together instead here. I will want to end this meeting. Yeah.